The interesting thing that we are going to explore now, which causes a lot of confusion for a lot of students, and one of the key points that I want you to take away from this session is the difference between the capacitance of a capacitor, the reactance of a capacitor, and the impedance of a capacitor. Now, if you have a level one understanding, basic fundamental understanding, and you are reliant exclusively on the reference handbook for the formulas and from the definitions and for the explanations, you will most likely not be able to make a distinction between these three quantities. I'm going to repeat one more time. Capacitance of a capacitor, reactance of a capacitor, and impedance of a capacitor. Okay. Capacitors are interesting because, again, they make us slow down a little bit, stop a little bit, because when we have capacitors connected in series, the net capacitance, the equivalent capacitance, the total capacitance just does not add up like it does for inductors and resistors. That is one minor challenge, one minor issue that we have with capacitors. Okay. So we have to actually add the reciprocals. It's as if these capacitors are behaving like the resistors in parallel. So capacitors in series act like resistors in parallel. Capacitors in parallel act like resistors in series. So this is a minor issue, not a big deal, but please, when you encounter capacitors, slow down and remind yourself that you have to take care of this. When we are talking about capacitance, okay, in simple terms, capacitance is actually a physical feature. Okay, in fact, we have equations that relate the capacitance with the distance and area and so on. It is a physical property. Okay, specifically, capacitance is actually the ability to hold charge. Okay, the ability to hold charge. So when we have lots of capacitors connected in series, the overall ability of this group of capacitors to hold charge is going to actually increase. When we have capacitors connected in series like this, sorry, this is parallel, right? And the behavior is like series for resistors and inductors. When we connect these guys in series, the overall capacitance is actually less than the smallest capacitor. So that's what capacitance is, pure and simple. It is just the ability to hold charge. Now, the confusion arises as to what happens when we have the reactance and what is reactance, right? This is reactance X, the X component. And then what is the impedance of a capacitor? The impedance of a capacitor is given by this formula, okay, minus J times XS. So it takes this form, and all of these formulas are given in the reference handbook. So the reactance of a capacitor, as we were discussing before, actually captures the effect of frequency. Okay, remember when we were talking about increasing the frequency, reduces the impedance. That effect is being captured by the reactance. Okay, and when we reduce the frequency, the impedance increases. If you bring it all the way down to 0 Hertz, the impedance of a capacitor goes to infinity. Okay, so all of that is being captured by the reactance of the capacitor. And now the third element, which is really the title of today's webinar, is impedance of a capacitor. And that's basically what confuses most of the students. If I tell you that I have three capacitors, okay, three capacitors that have impedance Z1, Z2, and Z3, and I ask you to find the total impedance of those capacitors when they are connected in series. Are you following me? Okay, so I have ZC1, ZC2, and ZC3. I want to connect these guys in series. Okay, all three of them in series. What will be the net impedance of ZC1, ZC2, and ZC3? What do you guys think? Will it be the sum of the three impedances? Or will it be the reciprocal sums of the parallel arrangement. It's either or, right? You are either going to add them up all together as impedances, and impedance has a value of ohms, correct? Or you are going to do the reciprocal formula. I'd appreciate if you guys can share your answers, your responses by selecting everyone from the drop down, okay, rather than selecting host and panelists, because then only I get to see your responses. Right? The answer is that it is going to be the sum. Because when you talk about impedance of a capacitor, it doesn't matter whether the impedance is of a capacitor, of a resistor, or of a reactor. Impedance is impedance. You add the impedances in series by simply summing them up. Okay. And even if there is the impedance of a capacitor, you're setting them as parallel, you're going to use the reciprocal formula. All right. So I hope you guys understand and appreciate the difference between capacitance, the reactance of a capacitor, and impedance of a capacitor. Same story with the inductor. When we have inductor, okay, connected in series, it is a little bit more intuitive because inductors add like resistors in series, and inductors in parallel act like resistors in parallel. So you don't have to sort of slow down. You can basically just bulldoze through the inductors as they are. Now, inductance again is a physical property. Okay. And when we were talking about capacitance, capacitance was a property to store charge, whereas inductance is the ability to store magnetic energy or to form magnetic field. So if we say that I have a very large inductor, then that basically means the ability of that inductor to set up magnetic field, lots and lots of magnetic flux is large. And if we have a tiny coil, then that basically means that its ability to store magnetic energy in the form of magnetic flux is going to be low. That is inductance, and inductance can be expressed in the form of the number of turns, the length of this coil, and so on and so forth. Inductive reactance is capturing the effect of frequency that we saw before. Okay, the effect of frequency is very important to capture because that is what makes this as a reactive device. Okay, by increasing the frequency, then inductive reactance increases, and by extension, your impedance increases. By reducing the frequency, the inductive reactance decreases, and by extension, the impedance decreases. Now, same question. If I tell you that I have ZL1, an inductor with an impedance ZL1, another inductor with an impedance ZL2, and then another inductor with an impedance ZL3, I want to set them in series. Okay, what will be the net impedance? The answer is pretty simple. ZL1 plus ZL2 plus ZL3. Because we don't care what is under the umbrella of that impedance, whether it's a pure resistor, whether it is a pure capacitor, whether it is a pure inductor, or a combination of the three. Okay. Once you give it the label of impedance, then basically impedances in series are going to add like this. Impedances in parallel are going to add like this. We know that Z is equal to R plus JX, so they may contain a combination of R and X and whatever inside them, but as impedances, this is how they're going to behave in series. As impedances, this is how they're going to behave in parallel. Does it make sense? Any questions, any comments on this? All right. So as an example, if you are asked a question, the question says that calculate the driving point impedance or the input impedance of the circuit that is shown over here at a particular frequency. You have the cap with its capacitance. You have the resistor with its resistance. When we are looking into this circuit, we realize that we have a series arrangement of two impedances. Impedance number one is our resistor. Impedance number two is our capacitor. So as impedances, please pay attention to this, they are going to add in series. Clear? As impedances. So we add this plus this, take care of the frequency, and that basically gives us this result. Now in the final step, what I've done over here is I've basically converted, excuse me, I'm basically converted this in a standard rectangular complex form. The standard rectangular complex form contains j in the numerator, not in the denominator. Okay, so if your answer is a little bit different and if you leave it here, I mean, your calculator can do all of this in one step, right? But please remember that even when you're dealing with the reactance of a capacitor and the impedance of a capacitor, sometimes they carry negative values. And that's for this reason, because we want to express the final form, final answer always in a standard form of the complex numbers, right? So this is done by multiplying and dividing by j. So j times j becomes a negative number and minus j ends up over here. And that's basically how we deal with this. So the key concept over here that in sort of the last few minutes that I've tried to explain you guys is that when we are dealing with blocks that are labeled as impedances, don't read too much into it, because impedances in series are going to act like this regardless of what is the makeup of the impedance. Impedances in parallel are going to behave like this regardless of what the internal makeup of that particular impedance is. Okay, and this is one example. For social validation, I have students giving shout outs on LinkedIn, on Reddit, on Amazon. Just this morning, I conducted an interview for my YouTube channel. P Power student who took the exam and passed the exam in first attempt within a month. Okay, although it's a rarity, but the fact of the matter is that if you put in the time and effort, use a proper exam preparation resources, have proper plan and commitment level, it is totally doable. And tons of interviews on my YouTube channel as well.